Our next example says set up the integral that would find the volume of the solid generated by revolving the region bounded by y equals 2 times the square root of x minus 1 and y equals x minus 1 about the line x equals negative 1. So let's go ahead and draw a quick sketch of what we have here. So 2 times the square root of x minus 1, the transformations that are happening there for the graph of, or the parent graph of y equals the square root of x is it's shifted right 1 unit, and it also is being vertically stretched by a factor of 2. So maybe it looks something like that. And then x minus 1, it has a slope of 1 and a y-intercept of 0, negative 1. And they should intersect somewhere looking like that. And it would probably help us if we found where those two curves intersect. So let's go ahead and set our curves equal to each other. We can do that since in this scenario they're both equal to y, so I can set these equal to each other like that. I'm going to go ahead and I'm going to square both sides now. So what I'm doing is I'm squaring this, and I'm squaring that. And the left-hand side, if I squared that, it would give me 4 times x minus 1. And if I FOILed out the right-hand side, we'd get x squared minus 2x plus 1. I'm going to go ahead and distribute on the left-hand side. And now I just want to get all the terms to one side. So I have x squared. I'm going to subtract 4x from both sides, so that would give me minus 6x. And then I can add 4 to both sides, so that would give me plus 5 equals 0. If I factored this, that would give me x minus 5 times x minus 1 equals 0. And we end up getting x equals 5 and x equals 1. So this value here is 1, and then this value here is 5. Now, I want to reflect this about the line x equals negative 1. So here's x equals negative 1. And I want to reflect about this line. So now I'm going to go ahead and reflect that. Try my best to make a mirror image here. So maybe it looks something like that. And notice that if I take my cross sections, they're going to be stacked vertically. So I have something like that, and then something like that. And each of my cross sections is going to be a washer or a donut in this case. Because I'm stacking my washers vertically, that means that we need to integrate with respect to y. So something that's going to help us is I can see visually that my bottommost washer will start at y equals 0, and the top one is going to end here. So I need to figure out what that intersection point is. I know that the x value is 5. So here in this equation, I'm going to go ahead and I'm going to plug in 5 for x. And if I do that, I get 4. So my y value here should be 4. That's going to be helpful when we are coming up with our limits of integration. So I went ahead and I kind of wrote our formula that we have when we're using the washer method and our washers are kind of stacked on top of each other vertically. So we're going to be integrating with respect to y because they're being stacked vertically, and we need to use the washer method because it's kind of our three-dimensional object, if you can imagine it, is hollow in the middle. So we need donuts or washers. So let's go ahead and think about our inner and outer radius in our picture here. So our inner radius is the distance from here to here. And this distance from here to the, let me be more specific. So the distance from the line x equals negative 1 to the y-axis, that's constant. That's always going to be 1. And then this distance from here to here, that is changing, and it is the x value of my square root curve. So what I want to do is, because we're integrating with respect to y, I want to take my curve here and I want to solve it for x. So let's go ahead and do that here. I'm going to divide both sides by 2, if we do that, we get y over 2 is equal to the square root of x minus 1. From there, I'm going to square both sides. So I'd get y squared over 4 is equal to x minus 1. And then from there, I can add 1 to both sides. So I would get y squared over 4 plus 1. And so that represents this x value right here. So my total inner radius, I need to take this x value and add 1 to it. So if I do that, then I'm going to be able to get that my inner radius is y squared over 4 plus 1, and that simplifies to plus 2. Okay, now let's talk about our outer radius, which is the distance from here, our line x equals -1, to our linear curve. And just like we had before, this distance, the distance from the y-axis to the line x equals -1, that's constant. That's going to remain 1. And then the distance from the y-axis to our curve, that is our x value for our linear curve. Now, our linear curve is y equals x minus 1, and I want to solve that for x by adding 1 to both sides. If I do that, I get x equals y plus 1. So now I can find my outer radius distance. So this is my outer radius, and it's equal to y plus 1 plus 1, which is equal to y plus 2. So I'm going to come back over here and say my outer radius is y plus 2. And now that I have that, I can go ahead and this question is just asking us to set up the integral. So let's go ahead and do that. So we have the volume is equal to, I like to factor out pi. You don't have to. You can keep it inside of your integrand. And our limits of integration, we're starting at y equals 0 and ending at y equals 4 because that's where our cross sections kind of start and end. If we think about stacking these slices of bread or donuts or washers on top of each other. And then we have our outer radius squared. So that's going to be y plus 2 quantity squared minus our inner radius squared. And then we're integrating with respect to y. So here is our final answer. And, it just asks you to set up the integral. If you are taking one of my classes, I'm okay with you leaving your integrand unsimplified like this. Example 9 says, set up but do not solve the integral that would find the volume of the solid generated by revolving the region bounded by y equals sine of x and y equals cosine of x on the interval from 0 to pi over 4 about the y-axis. So let's go ahead and draw a quick picture or graph. So I have y, I have x, and I know that sine starts at the midline, and because there are no transformations, our midline is the line y equals 0 or the x-axis. And what's nice is y equals sine of x and y equals cosine of x intersect when our input is pi over 4, because sine of pi over 4 and cosine of pi over 4, hopefully we remember from trigonometry that both of those values are square root of 2 over 2. So the sine might look something like that. And then cosine starts at the peak and then goes down from there. And so here, this value is pi over 4. And we are taking this region that we just graphed and we are reflecting it, or rotating it rather, about the y-axis. So I'm going to go ahead and try to reflect that image. And it's going to look something like that. And this one is interesting because we're trying to find the volume of this. And what's nice is that when we rotate this, it's solid in the middle. So we're going to end up using the disk method. And let me draw a disk. So here is one of my disks that I'm stacking on top of each other. The thing about this question, though, is that at some point my disk changes in terms of the radius, and that might look something different up here, and the radius of my disk is being dictated by a different curve. So with that in mind, in order to find the volume of this thing, we need to set up two separate integrals. Okay, so let's go ahead and start with the green disk that I've drawn here, and I want to find the radius of this disk, and that's essentially the distance from the y-axis to our sine curve, because this is y equals sine of x here. So we want that distance. Ask yourself, are we going to be integrating with respect to x or with respect to y? If you said with respect to y, you'd be correct because we're stacking our disks vertically on top of each other, and so the change is happening in y. So let's talk about the radius of the green disk. It's the x value, but because we are integrating with respect to y, we need to solve our curve for x, and if we do that, we end up getting x equals arcsine of y. So our radius for the green disk is arcsine of y. If we go and switch over to talking about the blue disk, that radius is affected by the cosine curve. So similarly, I want to solve that for x, and if I do that, I get arc cosine of y. So that's going to be our radius for the blue disk. And now we can go ahead and we're going to need to set up our two definite integrals. And as a reminder, we said earlier that this ordered pair here is pi over 4, comma root 2 over 2. And we need the root 2 over 2 so that we can create our limits of integration. So finally, our volume is equal to, if we stacked the green disks, then those would go from 0 to root 2 over 2. And then remember that the area of a disk is pi times the radius squared. So it's going to be pi times, and then our radius for the green disks, arcsine of y, quantity squared, and we're integrating with respect to y, plus our second integral will start from y equals the square root of 2 over 2 and then end at 1, because we know that the starting point for cosine is the ordered pair 0, 1. And then we have pi times the radius squared dy. And this here represents our final answer.